Okay, so a little bit about implementing languages on top of Erlang. There have been a number of talks here already about other languages running on top, and this is just a very simple, very general introduction, quite simple for it. So yeah, I don't know if you can see this. I know the problem, and if we have time for demo, I'll make my demo small near the top. Okay. So a bit of background. So when we were developing the language, there's a reason for the background. We were looking at the problem, which was telecom switches, and telecom systems, and we found the actual problem domain was a number of different points, amongst other these. So we had things like, he had to be able to handle a large number of concurrent activities, for example. Let's see if I can change the other pair of glasses so I can see something. You had timing constraints. Things had to happen at a certain time or within a certain time. That meant, for example, the system must never block. Because if some event occurs, it needs to respond immediately. We need distribution. If you want to build a truly fault-tolerant system, you need at least 2 computers. Continuous operation, yes, it should never go down. We need to be able to software maintenance without stopping the system, and it should have fault tolerance in it. This is your standard. This is the problem we were trying to solve with Erlang. This is what we're out to solve. And if you notice here, there is absolutely nothing about telecoms there. Okay. So where we end up on the first principles was, yes, we need lightweight massive concurrency, of course, to do this. We need the base for asynchronous communication as the base for all communication. And this is necessary for non-blocking systems. If you stay on a bit afterwards, I'll show you what goes wrong if you have synchronous communication in parallel systems. Process isolation, so when things crash, they should not ruin it for other processes. Not ruin the memory for it. We need support for error handling. And support for, we said, continuous evolution of the system, i.e. handling code at runtime. And we felt these measures, like, for example, the concurrency and the error handling, were so fundamental. These are really fundamental properties of the system. We had a few other things as well. We wanted a high-level language. So this is late 80s. So high level then isn't quite as high level today, but it's reasonably high level. We also had the criteria that we wanted the language and the system to be simple, right? Not complex. Simple in the sense you have a small number of the right basic principles, and on top of that you can build whatever you want, whatever form of complexity. But at the bottom level, it should be simple. And the language should be simple to understand and program. And yes, we can have a long debate about that, if it's simple to understand and program. But I can say this, if you look at the language, it is actually very simple. It's simple. It's much simpler language than most other languages people complain it doesn't look like. If I can, now I've said my piece on that. Simplicity is difficult. Complexity is easy, because if you just, something happens, just chuck in a new primitive, makes everything more complex. Simplicity is difficult. There's a wonderful quote by Dijkstra. He's made a number of quotes on this. So let's see if I can get it right here. Simplicity is a great virtue, but it requires hard work to achieve it and education to appreciate it. And to make matters worse, complexity sells better, right? So yes, so simplicity, we had this goal as simplicity. We also found provide tools, not solutions. Because, well, this is bitter experience. Sometimes we've tried to provide some solutions, but they were usually wrong. Right? So it's much better to provide tools for letting people build their own solutions on it. So if we look at Erlang, what do we find? Well, it's a simple functional language. It's relatively relatively high level. Yes, it's a different syntax, but all functional languages have different syntaxes. They're all weird. It's got your typical features of functional languages in it. We have lightweight massive concurrency. We have asynchronous communication. We have process isolation. We have error handling. And we have continuous evolution of the system, all this based into the language, right? This is sort of starting to look a bit familiar, isn't it? So yeah, that's the language. Now, if we go down one step and look into the BEAM, we find properties of the BEAM. And now it's starting to look very familiar. There are things for handling functional languages baked into the virtual machine. The lightweight, the massive concurrency is baked into the virtual machine. The asynchronous communication all of this stuff is in the virtual machine. So the virtual machine is designed to run Erlang. And all these things for it. The process isolation, the error handling, continuous evolution, handling of code, all this is in the virtual machine, right? We don't do global data. We don't do shared, we don't do mutable, and we don't do global. That's it, right? Again, this is all the way down. The soft real-timeness is in there. The non-blocking. The system, it's practically impossible to get to block the Erlang system. For example, there's a preemptive scheduler in there which handles a lot of Erlang code, right? You can do it, but you have to work at it, right? And, well, there's a lot of other features as well. We have a transparent multi-core handling. So the Beam will quite happily grab every core you give it, and it will balance load automatically over the system and do things like this as well. We'll also try and shut down cores if it feels that the load is quite low. And there's some very powerful introspection tools baked into the systems already. So this is the base of the Beam. And the Beam and the Erlang language is very closely integrated with each other. So the Beam implements Erlang. That's what it does, right? So if we're talking about languages on here, you have to remember this. Right? Yeah. So that just gets us to what we call the Erlang ecosystem. So it's languages built on top of the Beam, on top of Erlang, and on top of OTP. So we have a little box here for it. I don't think we have the box outside, but we have the box here. So we have the Beam here, we've got Erlang OTP there, based on top, and then we have a set of languages running on top of this, right? We have Erlang, of course. We have Elixir, of course, which does this. LFE, that's Lisp flavored Erlang. I like parentheses. There's a prologue running I've written as a Lua. There are a number of other languages as well. Now all these are running on top. And the thing here is, if they all follow the rules correctly, then they can all interact with each other. And your resulting system is going to be more powerful than each one. They can use all the features in there for it. So this is the important bit here for it. And did I get it wrong? Yes. Oh, bloody hell. Sorry. This one should come first. So extending the system. So now describe the basic ideas here. We have Erlang, we have OTP, we have the Beam at the bottom of this. I can just say now, so Erlang and the Beam interact. Erlang interacts downwards with the Beam, and Erlang interacts upwards with OTP. So the basic ideas behind that at the base of OTP, they were developed in the same time as the language, and the features of the language are there to support these things. So it's not a chance that linking is there, that Erlang supports links. So yeah, so extending the system, it becomes, you've got the old ceremony, you've got Erlang at the bottom, this becomes putting new skins on top of that, right? That, by the way, is a fantastic CD. It's your typical Leonard Cohen, extremely depressing, but it's a fantastic CD. So now I go back, I've got the ordering wrong here. So now, the way I see it, there are three basic different ways you can extend the language for it. And one, extending the system, and one I say here, I call it native languages. And they are languages which basically keep the Erlang execution model and data types, right? Okay. They can add a new syntax to it, which can be very different or very close, and they can have a lot of different packaging, but at the base level, it's just Erlang for it. And some examples of this, for example, Elixir. So Elixir, it's a skin on top. Sometimes it's a very thin skin, and sometimes it's a very thick skin, but at the base level, it's still Erlang for it. LFE, yes. Affine is another one. Clojure, there was a talk about this earlier today, which is implementing Clojure on top of the Erlang VM. There had been work on a number of statically typed languages as well, running on top. So, of course, Erlang is dynamically typed, and sometimes it'd be very nice to have a typed system, so there's work on statically typed languages. One is Alpaca, which is ML-based, and there are a few others as well. So, yeah, that's that. So these are the native languages. And the non-native languages, there you have to extend. You're not satisfied with how Erlang handles code and data. You have to extend this. And I'll give examples of two here. So there's a Lua, and there's a prologue. And I rather like Lua. It's a simple little language, but it has shared mutable global data. Everything we don't do, right? It has a completely different handling of code from Erlang. So if you tried to implement this directly in Erlang, you still have to do a lot of work to get this work. Prolog, so I have a Lua system I'll talk about. Prolog, there's a system Erlog. Again, it's different semantics. It has backtracking, it has unification, it has logical variables, which Erlang just doesn't have, right? And has very different handling of code. So it's very difficult to get a clear mapping between these. So what you end up having to do is to implement these languages on top of the Erlang system and put a quite fat layer in mapping how these languages handle things to how Erlang does it. So an example of this is how Luerl handles global data. It has a record here with all the global data, and when you're implementing this, you're chaining this through and you're mutating this global data. So from you're writing your Lua code, you're updating things and doing mutating and sharing, but this is all done here, so for example. So here we keep a track of tables. We keep track of frames. Some function frames have to be mutable. We have the global table, we have the stack, we have meta tables for data types. For it, we have a random number. Keep it so we can pass the random numbers around. We also have a unique tag for this implementation of it. The meta tables, we have meta tables for nil, boolean, numbers and strings. Yes, Lua provides all these things for you, right? Well, Lua has these things defined, so I need to provide that. We can have data types. So a record, a tref, that's a reference into the tables, the table. So this thing, the T tab here, is an array of tables. So a table reference is a reference into that data structure, the index for it. So if I go mutate a table, then anyone who references that table will see all the updates, which is how it works. It's shared mutable global. But I have to do that myself. I have to implement this on top of Erlang, because Erlang does not provide any support for this. And one of the goals here was to not mutate the Erlang system to do this. Tables, well, there's an array, apart from things for it. And we've got function information. So I have to implement all the Lua structures on top of Erlang to do this for it. So yeah, I'm not going to show you Erlog structures, but the idea is basically the same. I have to put a pretty fat layer which sits between my language at the top and Erlang at the bottom to give these things. The third one, which has also been talked about here, is you take your other language and put it outside somewhere. So you can put a port to it. You can run it as a separate operating system process and just communicate with that by sending messages backwards and forwards. You can run any language there. You can use NIFs. That allows you to write code in C, which you can call from Erlang as if it was, from the Erlang point of view, it looks like Erlang. It's quite nice. There's support for threads in there. And we have something called C nodes, which is sort of in between. It allows you to take an external operating system process through a port, and from the Erlang point of view, it will look like a distributed Erlang node. So I can send messages to it backwards and forwards for it, which is quite nice. There's some examples here, Erlang and J interface. So when should I choose which, right? So if we're going to native languages, this is the optimal use of the BEAM. This is as fast as you can get the BEAM running, right? Because it's doing exactly what it's supposed to do. It's the fastest, it's conceptually easy to interface, it's basically just Erlang, so I can call between the languages. I mean, if you're running Elixir, you can call Erlang. If you're running Erlang, you can call Elixir just straight through for it. And it's safe. Safe in the sense that you cannot crash the system by doing anything wrong here. You might crash your Erlang process, but that's okay. Downside, of course, is, which is, sorry, came a bit low here, it's restricted. Your language is Erlang, or very Erlang-like. It might look different, it might have different features, but it is basically Erlang at the bottom level. That's what we're saying here. And you usually need a large environment to be useful. You need libraries, tools, and things like this for it. There's nothing strange about this, but this is what you're doing. The next level up, if you're doing non-native, well, there are no restrictions on the language. It's a reasonable use of the BEAM, And if you do it properly, you can get, seeing we're implementing this in Erlang, we can get fast data transfer with Erlang, and it's safe because I'm running Erlang code. Might be implementing my language, but from the Erlang point of view, it's just a program. But it's generally slower than the normal implementation you'll have of that language. It's the price you pay for it. And it can be costly to implement it for it. It'd be quite a lot of work getting it right. And you need an environment. That's what the data structure I was telling you about for the non-Erlang features, the global data, the immutable data, etc. You have to do that. And the final case is the external systems. Well, you can access anything. Anything running out there, you can access it for it. You can monitor and manage systems, whatever you do for it. They're just from the Erlang point of view, they're just either operating system processes I can look to and communicate with. And do the maximum efficiency available by the other system. Generally, the interface is slower. That's something I have to pay for. Unless it's a NIF, when it can be quite fast. And it can be either safe or unsafe. Safe in the sense that if I'm running in this external operating system process and something goes wrong in that system, that will just crash the operating system process, and the worst thing that I'll see in my Erlang is that the port closed, right? But it will not crash Erlang. If I'm running it as a NIF, then you're on your own. If you make a mistake in the NIF and it crashes the system, you take down the whole Erlang system. So here it's a trade-off. Do I want speed, interaction? What do I want? What am I willing to pay for it? So they're saying external is safe and internal is unsafe. And now I think I've hit my time limit, haven't I? Yes. That's basically it. So yeah.